Hey guys, welcome. Yeah, so our last convergence test here. And as this is example 0, we're going to state and prove the root test. So first, the statement. So given an infinite series like this, what we do is take the limit as n goes to infinity of the nth root of the absolute value of a sub n. And look at that, right? So this is what I'm saying. So we take the limit as n goes to infinity of the nth root of the absolute value of a sub n, and this here, if we so choose, we can write like this. And in fact, in practical examples 1 through 3, I will utilize this version, right? Okay. Anyway, if we call this limit the number L, well, then if L is less than 1, then we say that the series is absolutely convergent. And of course, if it's absolutely convergent, then it's convergent. And if L is greater than 1, then we say that the series is divergent. And if L is equal to 1, then this series is either convergent, absolutely or otherwise, absolutely or conditionally. By otherwise, I mean conditionally. Or it could diverge. So if L is equal to 1, the test is inconclusive and we must use another test. Yeah? Okay. All right. So we're done stating it. So let's prove it. So here goes. So first, let's consider when L is less than 1. So when L is less than 1, right? When L is less than 1, we should be able to fit a number R between L and 1 because L is less than 1, right? Because L is less than 1, we can fit in or choose a number R between L and 1. That way, L is less than R is less than 1. Yeah? Okay. All right. Now, remember that L is the limit of this, right? The limit of this, right? That's L, right? Okay, and in this format too if we want, right? Okay, so now since taking a limit of this as n goes to infinity means like picking larger and larger numbers, which will make this quantity closer and closer to L, right? Like since that's what we mean by the limit is n goes to infinity, we should be able to pick a number capital M such that for all numbers little m bigger than capital M, we have that this here, which is the same as this here, is arbitrarily close to L, right? And so if we can make this here arbitrarily close to L by picking a large enough numbers M, and therefore, for a set that cutoff number capital M. But yeah, by picking large enough numbers, since we can get arbitrarily close to L, we can fit in this guy between L and R. This here, we can make it between L and R because we can get arbitrarily close to L, right? Okay, this is important that you understand that. And if you don't, you can ask me questions in the comments section about it. All right. But yeah, because we're able to fit in this quantity, right, between L and R, it means that this here is less than R. But wait, this statement here is equivalent to saying that, right? Okay, and guess what we're going to do now? We're going to make an infinite series out of R to the n. But remember, since R is less than 1 and bigger than L, R is between 0 and 1, right? And therefore, when we make an infinite series out of R to the n, right, like this, this is going to be convergent by the infinite geometric series where R is between 0 and 1, yeah? Okay, all right, so this here is convergent because it's an infinite geometric series that converges as R is between 0 and 1. Yeah? Okay. But we said here, right here, that the absolute value of a sub n is less than R to the n. So if this is convergent, then we can use the direct comparison test, also known as simply the comparison test, to make a series out of the absolute value of a sub n and claim that it converges. Because if a series made of this guy converges, then a series made of this guy will also converge. Yeah? Okay, cool. That's by the direct comparison test, aka the comparison test. But now, because, and by the way, like an important note is here, we can only claim that this series made of the absolute value of a sub n is convergent when we start the series at n equals capital M, because this inequality holds only when we pick values bigger than M, right? So this is going to be convergent. In other words, this is not going to hold true for numbers less than capital M. So we cannot claim that this infinite series converges if we start at n equals 1. But this is a legit claim, right? Okay, that's important note. But what we want to show is that the series made of the absolute value of a sub n from n equals 1 to infinity converges. But wait, the series made just like that, which is starting at n equals 1 to infinity, we can break into n equals 1 to capital M minus 1, right? And then pick up from there with capital M to infinity, right? This here is equal to this, and that's just properties of sigma. I have lots of videos on sigma, so you can check them out. But yeah, this is easy enough to understand, right? Okay, but wait, we said that this converges, right, from the comparison test, right? We said that it converged here. So if this converges, this is surely finite, right? And so we have a finite number plus some other finite number as this converges, and therefore this converges. Yeah? Okay, cool. So since a sub n in absolute value is convergent, we say that it's absolutely convergent. Well, okay, if it's absolutely convergent, then it's automatically convergent. That is, even if we discard the absolute values, we'll have that a series made of a sub n will be convergent. And that's what we wanted to show, right, for the case L is less than 1. So we're done here for the case L is less than 1. So let's consider the case L is greater than 1, where we want to show divergence, right? Okay, so when L is greater than 1, right, here there's some number, again, capital M, that we could pick, so that for all numbers little m bigger than it, we have this, which is that we have this here could be made bigger than 1, right? By picking numbers sufficiently large, we can make this bigger than 1, because L is bigger than 1, right? As we can get arbitrarily close to L, since, again, the limit here is equal to L, right? Which means that we can get arbitrarily close to L, we can pick large enough numbers so this is true. But wait, this is true means that this is true, right? Okay, and where to from here? Well, then that means that in here, this is true, which is that, like, if the absolute value of a sub n is greater than 1, then for these numbers, then it must mean that the limit as n goes to infinity of the absolute value of a sub n is not equal to 0, right? But wait, that means automatically that the limit as n goes to infinity of a sub n is not equal to 0. But then that means that using the divergence test this time, we can say that this infinite series is divergent. Yeah, and we say that again by the divergence test. If you don't know what the divergence test is, I have a video on it, so check that out. And if I haven't mentioned it, I also have a video, and several in fact, on the direct comparison test, simply known as the comparison test. So you can check them out, and I'll link them below this video. Yeah? Okay. All right. And as we said, when L is equal to 1, the test is inconclusive. So anything can happen, meaning the series can be absolutely convergent, conditionally convergent, or divergent. So let's look at situations where L is equal to 1 and where all three things that I just said will happen. And for you to see the three different cases and using examples, using three series as examples, you need to know that this is true, right? Like, I'm not going to show you in this video why L is equal to 1 using the root test in these situations, but it is. And in order for you to be able to see that L is equal to 1 in all of these situations, you need to be able to understand that the limit as n goes to infinity of n to the 1 over n power is equal to 1. But yeah, you can do it yourself, and maybe, you know, if there's enough demand, I'll make a video showing you why L is equal to 1 in all three of these cases. But yeah, here, this one is absolutely convergent, and this one is divergent, and this one is conditionally convergent, right? Because it doesn't converge an absolute value, but it does converge as is, right? So as I said, when L is equal to 1, anything can happen. Yeah? Okay, cool. All right, this is it for example 0 of the root test. And as I mentioned at the start of this video, there will be 3 practical examples. And the 3 examples, if I do well, will be representing the 3 different cases. Yeah? Okay, all right. I hope you enjoyed this and keep watching. Take care.